Hi children, this slide presentation explains collective systems and biological self-organization. Collective systems exhibit collective phenomena or collective behavior which provides an adaptive function that is not available to the individuals operating in isolation. Examples are a group of people walking through a shopping mall on a Saturday afternoon and a school of fishes that aggregate in the presence of predator. In both cases, the behavior of an individual is affected by the behaviors of its neighbors. But in the first case, the collective characteristic or the movement is worth studying for improving the sales or preventing accidents. But the second case, it provides an adaptive functionality to the participating individuals or to the participating agents. And collective phenomena can range from coordinated movement to nest building, and sometimes some kind of communication can be treated as a collective characteristic. And these phenomena rely on simple rules and local information. They do not require any kind of global plan or central coordinator. Now let's see the biological self-organization. So biological self-organization is a process where local interactions among simple particles or agents, they generate a structure at the higher level. Examples are the appearance of geometric patterns in reaction diffusion chemical systems and the formation of snow crystals. The resulting global patterns that we can see in snow crystals are said to be the emergent one because they are more than the sum of the constituent parts. And the resulting structures or the functionalities based on the collective phenomena, they exceed in complexity of the perceptual, physical and cognitive abilities of the participating organisms. Examples of biological self-organization are the construction of beehives, the foraging strategies of ants, and the regulation of colony life in social insects like ants, etc. So in all these cases, the resulting structure emerged from their collective behavior is the result of the collective work of individual organisms that execute simple behaviors based on local information, and they do not possess any global plan for the end result. And self-organization is based on two forces, attraction and repulsion, or we can say positive and negative feedback. Then what is meant by a feedback? Feedback occurs when quantity in the system is fed back to the system to increase or decrease the magnitude of that quantity. So the quantity can be density of individuals in a group. So small density produces attraction in order to increase the density, while the high density produces repulsion behavior to decrease the density. Anyway, the self-organizing systems, like any other system, it tends to have an equilibrium state. It is an interplay between positive and negative feedback. So on the way to the equilibrium state, self-organizing systems display multiple states and chaotic trajectories. So self-organizing systems can be described as a set of differential equations where the change of a system state is a function of the system state at the previous time step. It is taken as the positive feedback times a limiting factor. That limiting factor is a negative feedback. The magnitude of this limiting factor is inversely proportional to the magnitude of the system state. The self-organization systems with positive and negative feedback show some sudden modifications called bifurcations. We can understand what the bifurcation is through an example. So this slide shows an equation which describes the evolution of population size n. That is, nt plus 1 is rnt of 1 minus nt, where n is the population size. So from this equation we can have some facts, or we can extract some facts. The first one is, it produces a gradual extinction when the parameter r is smaller than 1. and we can see a growth to a constant value if the value of R is between 1 and 3. But it oscillates between two different population sizes if the value of R is greater than 3 but less than 3.4. And multiple states are possible if the value of R is greater than 3.4. That quickly displays some chaotic trajectories, and the population can transit between several unpredictable states but not the random sizes. Then comes the stigmergy. The stigmergy is also a collective behavior, or it is called a cue-based communication behavior, but it is not intentional. So it is called a type of social communication through modification of the environment. That is, the work done by an individual affects the action of another individual. And it was first developed by Grace in the year 1959 to explain the construction of the nest architecture by termites and other insects. Later, it is used to explain the foraging strategies of ants that deposit the pheromone trails in order to forage the food. Now let's see some examples of self-organization that inspired the computational robotic models. The first one is aggregation. So aggregation is a self-organization technique. It can be explained by positive and negative feedback, and we can understand the collective aggregation behavior using an example of fish school. So in fish schools, we can see large number of individual fishes. They swim in close formation that can rapidly change their direction, as well as they can disperse and reunite. So this kind of coordinated, homogeneous and rapid movement of the school gives the appearance of a single superorganism. It gives the illusion of a single superorganism. So a fish can display these behavioral reactions based on the position and orientation of other fishes. We can list 4 such scenarios. First one is, if there is another fish in its immediate neighborhood, the individual fish under consideration will move away to avoid the collision. That is negative feedback. If there is another fish at an intermediate distance, then that individual fish will tend to align along its orientation. If there is a fish at a greater distance, then the individual will tend to swim towards it. If there is no fish in sight, then the individual fish will perform random search movements. The next collective behavior is clustering. So several ant species, they engage in clustering and sorting collective behaviors. Examples are the corpses of dead ants are organized in large clusters at the periphery or near the walls of the nest for better circulation. And sometimes sand pellets are clustered to form a circular wall that protects the colony. And we can see eggs are organized in regular patterns where the neighboring eggs have similar maturation times for more efficient way of collecting the eggs. Then these are all the simple behavioral models that combines positive and negative feedback. So the probability that an ant picks up an object is inversely proportional to the number of objects it experienced within a short time window. So the ant will tend to pick up isolated objects. It won't remove objects that occur in clusters. But the probability that an ant deposits an object is directly proportional to the number of perceived objects in a short interval of time. That is, the ant will more likely to deposit object near the larger clusters of objects. But sorting behavior can be explained by adding different response probabilities for different types of objects in the environment. The next collective behavior is nest construction. It is exhibited by termites and wasps to collectively build their nests. So a number of models are based on positive and negative feedback that these models can be realized without a master architect. So all these models, they rely on some kind of stigmergic communication where the perception of the result of the previous work, that it triggers the construction behaviors which are genetically encoded as a stimulus response associations. That is, the work done by an individual unintentionally will act as a stimulus for constructing the structures in the next step. So this slide shows the pictorial representation of the idea that we have just explained. So it shows the successive steps in the construction of a structured lattice architecture, which includes a pedicel external envelope, regularly spaced layers of columns, and an entrance opening. The completion of each step gives rise to a stimulating configuration to build the next one. The steps 7 to 9, the front and right portions of external envelopes have been cut away to show the inside of the structure. The next collective behavior is foraging. Here also we can use the properties called stigmergy, which can improve the efficiency of this collective foraging technique. So some ant species, they lay pheromone trail which can be used to select a path, select the shortest path to establish a link between the food area and the nest. So it was studied by Duenberg et al. And they come up with some results. When pheromone laying ants are presented with two alternative paths of equal lengths between the nest and the food area, initially they distribute, all the ants are distributed equally between two paths, but after a few minutes most of the ants travel only through one of the two paths. So this slide shows the pictorial representation of the idea that we have just explained. So we can see the pheromone depositing ants tends to choose one of the two available paths between nest and food. So the path that is initially visited by more ants contains more pheromones, which attracts more ants, and it is reinforced positively, which can increase the pheromone quantity. So that path will be selected as the shortest one. But if the ants are presented with two paths of different length, they will tend to choose the shorter one, because ants on the shorter path can return earlier to the nest, and so it leaves more pheromones on that path. It will attract more ants, so the shortest path will be selected. So if considerably more ants choose the longer path than the short path in the early stage of exploration, then they will stick on to that longer path. But the computational models inspired by this ant foraging technique, they solve this issue by assuming the fast evaporation of pheromone trail, which favors the choice of the shortest path. Then the Duenberg et al. They studied the system that the positive feedback mediated by the pheromone deposition that can help the blind army ants to raid through large territory in search of prey while maintaining their path to the nest. So it shows some different raiding patterns if it is raided by different species of army ants. But this different pattern is not because of the different searching rules of this army ants, but it is because of the different dispersion patterns of the prey. So it is shown in this diagram. So the army ants explore the environment in search of prey while maintaining their paths to the next with pheromone deposition. we can see some different patterns, foraging patterns. So it depends on the pattern of scattering of the prey. It is not because of the different rules they adopt to get to this prey. It is only because of the different patterns of scattering of prey. Then comes the division of labor. So the self-organizing techniques that we have discussed so far depends on the same set of behavioral rules, or they perform same activity. But several of the insect societies, they display division of labor and specialization, where different activities are simultaneously performed. So individuals can be specialized in soft and strong manner. Then what is this soft and strong specialization? Softly specialized individuals are the individuals that can perform several jobs, but at every instance they tend to perform the activities that is most needed by the group. But strongly specialized individuals, they can perform only one job, most of the time a few activities. Examples are foraging and nest defense in ants, foraging and nursing, nectar and pollen collection in honeybees. So in such systems, there comes situations of unpredictable situations of modifications of the environment, and there comes variability within the colony. So in such situations, it requires some additional mechanisms for ensuring the dynamic task allocation. Example is that some ant species, they are specialists of type A. They can carry out the tasks that they would normally not perform if the number of specialists of type B for those tasks decreases. So to implement this dynamic task allocation, we can use the response threshold model. This response threshold model was put forward by Bonabio et al. In the year 1996. So this model, response threshold model, explains that an individual performs a task if the stimulus associated to that task exceeds the threshold. Examples are the demand of water is a stimulus associated to water collection, and the number of enemies in the surrounding of nest is a stimulus associated to the nest defense. So an individual with the low threshold will tend to perform the corresponding task even if the stimulus is very low. But an individual with high threshold will perform the task only if the stimulus is very high. So the response threshold model explains the regulation of essential elements such as food by allocating individuals to forage as soon as the food demand increases. So individuals can have many different thresholds as the many different tasks are required for colony survival. We can explain the dynamic task allocation using a scenario. So it can be explained by assuming that specialists of type A have low thresholds for the stimulus associated to task A and moderate threshold for task B, where specialists of type B have low threshold for stimulus associated to task B and high thresholds for task A. So as soon as the number of specialists of type B decreases, the stimulus associated with that task will increase until it exceeds the corresponding thresholds of specialists of type A. So consequently, some specialists of type A will start to perform the task of B until the corresponding stimulus falls below the threshold. Then comes the swarm intelligence. Swarm intelligence is also a collective behavior, and it is an area of research. Studies large collections of relatively simple agents that can collectively solve problems that are too complex. So for a single agent, it can display the robustness and adaptability to the environmental variations that can be displayed by a biological agent. That is, simple agents can perform complex jobs using the collective behavior or the collective characteristics. Thank you.